Hello, welcome back to your Bridging Mathematics, Analytic Geometry. Okay, so let's discuss the final unit for this module 4. Okay, the conics or the conic sections. Okay, the conic sections. So, what do we expect in this unit is for us to know the types of conic sections. Okay, so what are these conic sections? And then, of course, to know the general and standard forms of these conic sections. Okay, and then of course to solve problems involving conic sections. Okay, so in the first place, what is a conic section? Okay, so a conic section is a locus of a point which moves so that its distance from a fixed point, which is called focus, is a constant ratio to its distance from a fixed line, which is what we call as the directrix. And then that constant ratio, okay, this ratio of the distance to the focus and the distance to the directrix, okay, that constant ratio is called the eccentricity. Okay, that is called the eccentricity, which is denoted by variable e. Okay, that is our eccentricity. Okay, so here are the types of your conic sections. Okay, by the way, conic sections are second degree curves. Okay, just like circle, these are second degree curves. So we will also be following the general form of the second degree equations or second degree curves. Okay, so we have here your first type, your parabola. Okay, parabola. The eccentricity of that is equal to e. Okay, always. So that is the uniqueness of your parabola. For that to be parabola, the eccentricity of all the points or the ratio of the distance of all the points to the focus with the directrix is always constant, which is equal to 1. It means that the distance to focus and distance to the directrix are the same, so that your ratio is 1. Okay, so that is parabola. So this is the example of your parabola curve. Okay, and we have here the central conics. Okay, by the way, why do we call this one central conics? What is the difference of that with the parabola? Okay, the central conics has now a center. Okay, we will be discussing later on the parts and the parameters of these curves, but let me just discuss to you what is the general or the general difference of this parabola and the central conics. Okay, so in central conics we have here two types. So central conics, if there are, since that is actually literally having a center. So first there is the ellipse. That is just like a circle, but of course the radius in all throughout the distance are not equal. So that will now be what to call this one, following a shape of an oblong. And there is a center here between all those points. So that belongs in your central conics, and that will happen only if your ratio, your constant ratio or your eccentricity is less than 1. Okay? And then what if that eccentricity is greater than 1? It will still be a central conic since there is still a center, but the center is actually not literal at the middle of the curve, because actually if you will try to look at this, the hyperbola, we call that one the hyperbola. This is the curve, and the center of that is, we have it here in between them, but not exactly at the center of the points, because of course they are opening opposite. So it is just like, if you will try to cut the ellipse, it is just like an ellipse that is facing, it is just like the half of ellipse facing back to back each other. Okay, so that is hyperbola, and that will happen if the constant ratio eccentricity is greater than 1. So again, we are just actually having here a conic section, since we are governing that one, or we are trying to define that one based on the ratio of the focus of the distance of all the points of any points on the curve from the focus and from the directrix. We call this one the directrix. A fixed line is the directrix, a fixed point is the focus. Okay, so if your eccentricity is equivalent to 1, that is parabola. If that is less than 1, that is a central conics, which is what we call as the ellipse. And if that is greater than 1, that is another central conics, which is we call as the hyperbola. Okay, so we will now discuss this one by one, detailed in these next slides. Okay. So let's start with your parabola. Okay, so a parabola is the locus of points which are equidistant from a fixed point, focus, and a fixed line directrix. So as I've explained a while ago in the previous slide, that the ratio, okay, since it says there that a parabola is having a point which is always equidistant. If you say equidistant, equidistant means the distance, okay, is equal. Okay, so the distance of any point on this parabola to the focus and the distance to any point any point on this parabola to this fixed line, which is directrix, is equal. It's always equal, equidistant. So that is the explanation why we have there the ratio which is equal to 1. So if you'll try to, okay, this is the shape of that. So let's say this is the parabola. If I will try to consider here, a point, let's say I will consider this green point. And we have there a fixed point, which is actually, we call this one as the focus. Let's denote that one as F. And then we have there a line, fixed line, which is, we call this one as the directrix. So if I will consider any point in this curve or in this parabola, I will consider that and get the distance. Okay, the distance to the line that we are considering is of course the shortest, or that is the perpendicular distance. So that distance to the line and that distance to the focus, if I will get the ratio of that, okay, let's say that is m, that is n, m over n, since they are equidistant always, according to the description of parabola, they are always equal to the distance. So if they are always equal, then the eccentricity of that's why we had the eccentricity of a parabola equals 1. Okay. Again, what is eccentricity? That is the ratio of the distance of any point on the curve to the focus and to the directrix. Okay, now, again, m and n in all points of these are always equal, so you have their eccentricity equals 1. So, let's try to discuss about the equation of this and then the parameters of that. Okay, so again, let's try to recall before, as I've discussed this one before. The general equation of a second degree curve is this one, isn't it? Ax squared, by squared, cx plus dy plus e equals 0. It doesn't matter if x is not there, x squared is not there, y squared is not there, x is not there, or y is not there, as long as there is one squared variable. As long as there is one squared variable, that will create us, or that will give us a curve, a second degree curve. Okay. So general form of a parabola. Okay, in circle. Okay, if you will try to recall, this is actually a continuation of a second degree curve. So our very first type, or a perfect second degree curve, is the circle. That will happen if your a and b are equal, your coefficients of x squared and y squared. How about your parabola? When do we have a parabola in your second degree curve? If, okay, that will only happen if a is 0 or b is 0, or in short, one of these doesn't exist. Okay, so for example, a is 0 or x squared doesn't exist. So you have there only y squared, it could be x, y. Then this is a second degree curve, which is parabola. Or if b is 0, so we only have there x squared, but there is no y squared, that is still a parabola. So that is your way of recognizing if your equation is parabola or not. If only one variable is squared, that is parabola. Okay. So there are two actually possibilities of your parabola. Actually 4, but let's try to divide it generally into 2. So by merely looking, if your x is squared, so what does that mean? Y is linear and x is squared. So what does that mean? In one value of y, there are two values of x. So if you'll try to look, this is an example of that. Okay, let's say I will consider a one value of y. Let's say in this level, in this value of y, isn't it? Let's say somewhere here is, let's say that is y equals 5. There will be two values of x because there are 2 points that we will be having in your curve, isn't it? In this level, there are 2 points, this point and the point there. So you will expect 1y and 2x. So pair the y with the first x, that is another point. Pair the y again with the second x, that is another point. So that is the meaning of that is the interpretation of your squared and linear exponents. Okay, so again, so that happens in every value of y there are 2x. So in this y there are 2x, in that y there are 2x, in this y there are 2x. So tracing this one, that will actually form a curve that is opening upward. That's why if your x is squared, that is a vertical. And there is another possibility for this. This could be still opening vertically, okay, vertically, but it will now be opening downward. It will now be, the curve will now be opening downward instead of upward. Okay, so later on I will discuss when do we have an opening upward, or when do we have an opening downward in your vertical parabola. Okay, so that explains now also the second possibility. If your y is squared and x is not, since again that is parabola, only one should be squared. So if y is squared and x is not, what does that mean? This is actually not the drawing of that, but I will explain it here. Okay, in each value of x, so let's say in each value of x, in this value of x, there are two values of y. So it means there are 2 points in one value of x. And another value of x, another 2 points, another 2 points. So if you will try to connect that one, it could be a curve opening to the left, or it could be a curve opening to the right. So that is generally a horizontal parabola. So again, I will explain when this will be opening down to the left, or this will be opening to the right. So this is your general form of parabola. By merely looking at the general form, if only one variable is squared, it could be x or it could be y, then that is automatically a parabola. Okay? If x is squared, that is vertical. If y is squared, that is horizontal. Okay? If you forgot about that, just think of that there are two values of x and one value of y. So what does that mean? That will open vertical. It could be down or up. And you will try to look at this one. There are two values of y and one value of x, so that will be opening left or right. Okay? That is your general form. If you will try to rearrange this one, just like in circle, we have also what we call as the standard form. Okay? So in your standard form for circle, that is x minus h squared plus y minus k squared equals r squared. But in here, it is almost the same. But of course, just a little bit rearrangement. And the value of h and k is not a center anymore, because in your parabola, we do not have a center there. Okay? We do not have a center in parabola. Only what we call as the v, or that is the vertex. That is now your hk. So first is your vertical. So if you will try to rearrange this one, separate x and then get the perfect square, and then separate y and then arrange this one into this manner. Okay. So this is what you should be focusing. X should be again x only, and that should be y alone. So if you have a number paired with y and there is a constant there, you need to factor that number outside. That is actually a coefficient of your y, so that will be y alone. And whatever number paired with your y, make that one minus, and the number here is your k, which is your y coordinate. Again, the number paired with y is always y coordinate, paired with x is your x coordinate of what? That is your vertex of your parabola, that is this one. Okay, the vertex. So if that is opening downward, that is the highest point. Since this is upward, this is the lowest point. If that is to the left, that is the most rightmost part. But if that is opening to the right, that is your leftmost part. Okay, you can just figure that out. That is your vertex. So that will happen if that is vertical. Okay, so again, x is squared, so get the perfect square, and then make this one y minus a number. But, of course, if you will factor that out, you will have a number there outside. So that number here, okay, it could be a positive with negative. That is the meaning of your plus and minus. What do we mean by plus? Plus means, since that is a vertical, plus means if the number outside your y minus k is positive, that means that your vertical parabola is opening upward. So the sign here, actually the signs here determine the opening. As I've said a while ago, in your vertical, there are two possibilities, opening upward or opening downward. So if that is positive, the number outside is positive, that is opening upward. If that is negative, that is opening downward. Okay? And then, okay, what is this for a? By the way, we call that one latus rectum. Later on, I will explain what is that. Okay, so that is your vertical. How about if you're horizontal? So now y is your perfect square, and then x is to be separated alone, and factor out the number whatever is paired with x. And again, this is a horizontal, so as I've said a while ago, there are two possibilities, opening to the right or opening to the left. So now, how do you know that is opening to the right? That is positive. If that is opening to the left, that is negative. So just like your sign convention of the rectangular coordinates, guys, just like the direct sign convention of x and y axis. If that is up, that is positive. If that is down, that is negative. If that is right, that is positive. If that is left, that is negative. Okay? So again, you can, by merely looking at the squared variable, you can say if that is a vertical or horizontal. And for you to know which one is the opening, put that down into the standard form. And look at the sign of your, we call that one the latus rectum, the number outside. 4a, that is your 4a. Okay, so again, your v there or your vertex is the coordinate h and k. That should always be minus, just like in circle. And that f is in this our figure, that focus that we are referring to is your f here. And okay, how does that relate with the vertex and that latus rectum? Okay, let's try to relate this one. These are the so-called parameters, your latus rectum and your vertex and your focus. These are what you need. These are what you need if you will try to draw your graph manually first. Okay, so let's say you have there your vertex. In a parabola, a vertex, okay, if you will try to have there the vertex, actually that divide, there will be a line passing the axis, a major and minor axis that we are referring to. The major axis is what we call this one. The major axis is imaginary line which is dividing your parabola exactly in half. Okay, that is your major axis passing at your vertex and focus. And then we have a perpendicular axis to that, which is actually your minor axis. We call that one the minor axis. Okay, that is just to govern the opening of your parabola, or to show the symmetry of your parabola. Okay, so within this major axis, from the vertex lies your focus. Okay, from the vertex within the major axis lies your focus, which is at a distance a. That is a distance a. So if that latus rectum is equal to 4a, all you need to do is divide that latus rectum by 4 so that you will get the value of that a. And that distance is actually the distance of the focus to your vertex. And so the same distance from the vertex to the directrix. This is your directrix. This is the fixed line. Okay, so that means if that vertex to focus is a and that vertex to directrix is a, the total distance from the focus to directrix is twice a. That is for parabola. Our distance here is to a. Now, from the focus of the parabola, try to draw a line which is equivalent to 2a, to that twice a. It means the same distance going to directrix. Draw that one perpendicular to your major axis. You will intersect exactly 2 points on your parabola, and those 2 points, if you will try, of course, to get the distance of that, since that is 2a, that will now be our latus rectum, which is 4a. That is what we call as the latus rectum. So actually, what is this latus rectum? Okay, that actually determines how wide the parabola opens. So that is how important your parameter latus rectum, because you can decide by merely looking at that value of latus rectum, you can say that that will be a wide parabola or just a narrow opening parabola. Okay. So again, because if you will try to rearrange that one, what you can get actually here is just the vertex. But that number here outside your x minus h or y minus k, which actually contains the signs of your opening, that determines actually if it will open a very very wide parabola or a narrow parabola. Okay, so that is your latus rectum. So that is our parabola. Okay. So again, that plus and minus is the explanation that I explained earlier. So let's try to have the next one, which will be, before we will have an example, let's try to discuss all the conics, and then we will have an example in all of the, as a whole of these conics. So let's proceed with your ellipse. Okay, so what is ellipse? An ellipse is the locus of a point which moves so that the sum of its distances from the fixed point, which is what we call, okay, there are fixed points. There are two fixed points here. In your parabola, there is a single fixed point, which is your focus. In your ellipse, there are two focus. There are two focus. We call this one a plural form of focus is foci. Okay, is constant. Okay, so that means the distance from two fixed point is constant. So that determines if it is an ellipse or not. So when do we have an ellipse? If the distance of all the points on a curve, if the sum of all of that distances from focus 1 and focus 2 is constant, then that forms now an oblong shape, or that is what we call as the ellipse. Okay, so the constant sum is the length of the major axis. Okay, I will explain later on what is major axis, which is equivalent to 2a. The a of this is different from our a while ago. Okay, the a here is the distance of focus to vertex and vertex to directrix. That's why you need to know how to differentiate these types of conics. Okay, so again, what does that mean? There are two focus in an ellipse. So actually, this is an example of ellipse that is in the shape of oblong. And we have here a focus. Let's say that is your first focus, second focus. Okay, by the way, focus are always located on the opening of the curve. So again, just like if you try to cut this one, that is just like two parabola which are meeting together. Okay, this is just like a two parabola facing each other that will meet together, and then that will continue revolving and creating a shape of oblong shape. And let's say this first focus here governs the opening of your first half, and then the second focus governs the opening of your second half. Okay, so that is your ellipse. So again, when do we have an ellipse, isn't it? If you try to go back to our definition on conics, the ratio or the eccentricity, okay, again, what is eccentricity? The ratio of the distance of any point within the curve to the focus with respect to the distance to a fixed line, which is directrix. Okay, by the way, if there are two focus, that means there are also two directrix. Okay, so again, let's just try to focus on one of these. Since they are symmetrical, actually you can cut this one into 4, and that means if you are going to cut this way, this is symmetrical with respect to x. I mean, yes, with respect to horizontal. If you will cut that way, that is symmetrical with respect to vertical. Okay, so now before we will go to the forms and so on and so forth, let's try to discuss why is it that we will be having a less than 1 eccentricity in ellipse. Because again, if you will try to look at this, I will consider this green point here, any point by the way. So let's say I will consider this. The distance to the fixed point is your m. Say that this is your m. And then the distance to the fixed line is your n. That is our n. So if you will get the ratio of that, this will always be, okay, m is always less than n. Okay, wait. M is always, yes, m is always less than n. So if you will try to divide that one, because the ratio is according to focus all over the directrix, isn't it? Distance to focus all over distance to directrix, that is our eccentricity. So distance to focus is m, distance to directrix is n. So if that m is always smaller than your n, then you will end up with a smaller value, less than 1, smaller than 1. Okay, so that is true to ellipse. That is only true to your conics, which is ellipse. Okay, any point. And one more, okay, one more that will define the ellipse is that since there are two focus, considering here any point again, I will consider any point, but okay, let's consider different from that so that it will not ruin our figure. So let's say I will consider a different point, or any point, by the way. Consider this point, this orange point here. If you will try to get the distance to the focus 1 and focus 2 according to the definition of ellipse, for that to be ellipse, the summation of that S1, let's say that is S1 and that is S2, the summation of the S1 and S2 is always equal to 2A, which is actually the length of your major axis. So 2A, that is constant in any point. Okay, so I will transfer, let's say I will consider that point. The distance to F1, F2, if I will summate that one, that will always be 2A. Any point, let's say I will consider this one. Distance to this and distance to that, summate that one is always 2A. Okay, it is always 2A. So, what is that A, by the way? Okay, what is that A? If you will try to look at our parts, I define this, I label that one. Your 2A there is actually your major axis. Go to this one. Now later on we will discuss your equation. But this one, okay, 2A is the length of your major axis. So again, a major axis, our major axis in your ellipse is from vertex 1 to vertex 2. Okay, so again, that is just like two parabola that are facing each other. So these vertex are on these opposite sides. So the vertex of that first and then vertex of that second is actually the distance between them is what we call as the major axis, which is equivalent to 2A. So that means that from the vertex to the center of that is A, distance A, and the center to that other vertex is also distance A. That's why your major axis, this is our major axis, equivalent to 2A. We have the minor axis, that is the perpendicular, okay, that determines the width of your ellipse. This is the length of your ellipse, your major axis, and that is the width of the ellipse, which is the transverse. Okay, so that if that is B, this is B, and that is also B, of course, since that is symmetrical, your length of your minor axis is 2B. So your 2B there is equivalent to the length of your minor axis. So, what is A and what is B? If A is major, 2A is major axis, A there is semi-major axis. What do you mean by semi? That is half, okay? Half of your major axis, and then B there is half of your minor axis, or that is semi-minor axis. Or again, your semi-major is from vertex to center, that is A. Vertex to center, that is A. Okay? And then, of course, your B there is from center to the farthest distance perpendicularly to your major axis. Or that, again, is the half of your minor axis. Okay, so that is A and that is A and that is A. Ito, this one. The total length is A and that is B. Okay, we have another variable here, C. We have that one. That is a distance to the center going to focus. So isn't it that your A is center to vertex? We have another distance from center to focus. Center to focus is your distance C. Okay? That is your distance C. And of course, your distance from center to directrix is D. That is our D. So if you will try to compare that one with parabola, there are a lot of parameter on ellipse compared to parabola. And these distances from focus to vertex are not the same in all of the conics. They are different. Okay? Since again, your eccentricity are different. So again, this is your ellipse. Your A is vertex to focus, which is actually half of your major axis. Your B is the perpendicular to that, half of your minor axis, and then your C is center to focus distance. And then we have a D, which is center to the directrix. So that is symmetrical. So in the other side, that is also the same. Okay. So that is our parameters. F is focus, C there is the center, which is actually the coordinate HK. We will try to discuss that one. If we will go on the equation, I will explain that one later. But we have here the we have here the latus rectum. Okay, we have here your latus rectum. L. L is your latus rectum. L is your latus rectum, which is that again. That is the latus rectum determines how wide the opening is. So again, that is just the distance of 2 points which is aligned with your focus. So again, let's say I will consider that one, that is latus rectum. But this time it is not equal to 4a. That will only be true in parabola. 4a latus rectum is parabola. But in here, since a is a different definition, that latus rectum is not equal to 4a. Okay, so please do not be confused with that. Again, latus rectum is the distance of 2 points aligned with your focus. So again, if I will consider here this distance of 2 points aligned with your focus, 2, that is still the latus rectum, since they are symmetrical. Okay, so now let's try to discuss about the equation. General again of second degree curve. In circle, A and B should be equal. In parabola, one of them should be missing, or only one of them should exist. In ellipse, they both exist, but they will never be equal. And the same sign. If that is positive, positive, it should be positive. If that is negative, that should be negative. So again, A and B should not be equal, but of course, the same sign. Okay, because if they will be equal, then that will not be an ellipse anymore. It will be a circle. Okay, so again, that is your ellipse for you to recognize the general equation of that. So look at the coefficient of x square, y square. They should be the same sign but different values. That is ellipse. Okay, so we have this as general form. And if you will try to rearrange this one, so we have 2a squared, the x and y, so you will be applying 2, you will be doing 2, completing the square, but of course, the number here is not r squared, it will now be reduced to unity, just like your intercept form, isn't it? So what you will do is, apply completing the square for x, apply completing the square for y, you will end up here with a number. But that is not in that form because that will be only for circle. So we do not need that number here. So we will divide it by that number so that it will become 1. So it will divide both sides by that number. And then simplify. This will be a fraction. This will be a fraction. And then you will end up here with a number and get the square root of that. And that number is your a. And that number is, get the square root of the number below. The number is your b. Okay. You have a and b again. A is your half of major axis, B is your half of your minor axis. So actually, in parabola, for us to know if that is a vertical or horizontal, you can look at the x and y squared. It depends on which one is squared. For ellipse, that depends on whose denominator is bigger. Because if your denominator, okay, A is always bigger than B, isn't it? Since that is major. So if your half of your major axis is below x, that means it is elongating parallel to x. It is elongated with respect to x. Okay? It is elongated along x, I mean. So if that happens, that is this form. That is your horizontal. We call that one a horizontal ellipse. Again, it is elongated horizontally. But what if your a or your bigger number is below your y? Below your y? And of course, you will expect that your smaller will be below your x. Then what does that mean? The major axis is parallel to y. So that means if I will draw the ellipse, this is the opposite of this. It is elongated upwards, or it is elongated vertically. So that determines if that is if that is elongating vertically or horizontally. Okay, so that is our ellipse. And again, your number there paired with x and then number paired with y is the coordinate of center, just like in circle. Okay, again, the difference of this in circle is that you do not have a denominator there. What you have is a number squared here, because that represents your r squared, or your squared of your radius. Okay. So almost the same manipulating, just like your circle. Okay, so that's it for ellipse, but Let's try to relate since there are a lot of that. There are a lot of your parameters, so let's try to find the relationships. Okay, so this is our figure. So again, the vertex to center is A, focus to center is C, directrix to center is D, and then half of your minor axis is your B. But at the same time, in ellipse, okay, this will only be true to ellipse, that A here, that distance A is the same distance if I will connect this focus to that endpoint of your minor axis. If I will connect that one, that is the same distance as the vertex to center, which is A. So if that is A, that is also A. So that forms as actually a right triangle to relate the values of A, B, and C. But this time, okay, this time your A is longer than C. Unlike in your Pythagorean theorem, C is longer than A. But this time in this ellipse, A is longer than C and longer than B. So that means that your A is your hypotenuse. So applying your Pythagorean theorem, guys, from trigo, so A squared is equal to B squared plus C squared. So that is coming from this right triangle here. Okay, what else? Let's try to relate the D, A, C, and so on and so forth. So actually making use of your trying to satisfy the eccentricity, okay, isn't it that eccentricity is distance from the fixed point to the ratio of distance to the fixed point to the directrix? But actually we do not need that value. But if you will try to use that that definition, you will end up with two formula. Okay, you will derive that one, but actually I will not show you here because that will just take time. The derivation, you can see that one on books. Okay, so if you will try to use the definition of a point, which is the ratio of distance to the focus with the directrix, which is what we call as the eccentricity, you will derive that eccentricity is equivalent to A over D, the ratio of A over D. Your A is again your semi-major, and your D is your distance to directrix. So as you can see, A is smaller than D. So if you will try to get that ratio, that is smaller than 1, which is true in ellipse, isn't it? And then we will also derive this one, and you will end up with C over A. Your C is focus to center, A is vertex to center. That is equivalent to this ratio here. So, isn't it that C is smaller than A? So again, that will be less than 1, which is your eccentricity. So it depends on what is given. Maybe what is given is the eccentricity. You can solve D given A or vice versa. Or let's say you are given E, you can solve C or A, vice versa. So these are two equations. Or let's say you do not need actually E. Then all you need to do is pair A over D is equal to C over A. You will create another equation. Okay, and lastly, what else did we not yet relate is your latus rectum. What if we will relate this latus rectum to your, what do you call this one? To your latus rectum to the other variables? Actually, if you will try to create here another right triangle, but I did not show you here, that is again another right triangle, solving whatever that distances and so on and so forth there, you will end up here with, okay, you will end up there with this formula. The latus rectum is equivalent to 2 times the square of your semi-minor all over A. That is the equations that we will be using to determine the rest of the parameters in ellipse. Okay, this is important for you to know because we will go to the hyperbola. This will be almost the same. The only difference actually is this one. This is still true to your hyperbola. The only difference is your in this Pythagorean theorem equation. Okay, so that's it for ellipse. Let's try to proceed with your hyperbola. Okay, so if in ellipse the distance of the two focus of any point to the two focus, if you will summate that one, that is constant, which is equal to 2a, in ellipse, and I mean in hyperbola, that is instead of summating that one, instead of adding that one, that 2 points or 2 distances, we will subtract that one. We will try to get the difference. and that should be also equal to 2a. So that is hyperbola. We have this center here. So instead of this curve to be facing each other, they will now be facing back to back each other. They will now be back to back. So your focus 2 will go there, your focus 1 will go on the other side. So your center is still there. Okay, center is still there. And again, that will only be true for hyperbola if, let's say, I will consider here any point. Let's say I will consider this point here. Let's say this point, since that is where I wrote the definition. If I will consider this point, any point actually, but let's say I will consider this one, the distance to that first focus, let's say again that is S1, distance to the second focus, let's say that is S2. And then the difference of that, since that is hyperbola, we are referring to the difference. So the difference of S1 and S2 should always be equal to 2a, which is your major axis, or we call that one in hyperbola, we call that also as transverse axis. Transverse axis. Okay? 2a. 2a. So that is true in all the points. And by the way, if you will try to look at this, 2a is again distance. A is a distance vertex to center. Center to vertex. So again, if that is A, that is A, that is still 2a, which is again from vertex to vertex. Just like a while ago, vertex to vertex is A and A, so that is still 2a. But this time it is now facing back to back each other. Okay, what else? Let's try to verify your eccentricity. Why is it that we will be having a bigger than one eccentricity in hyperbola? Okay, I will consider this point. Any point again, but let's say I will consider this point. If you will try to again say that the distance of that point to that focus, get the ratio with the distance to the directrix, m will always be, in hyperbola, it's true to hyperbola, m is always bigger than n. Okay? But it doesn't look like in my drawing because maybe in my what do we call this one? What do we call this one? My scale is not the same for x and y. But if you try to draw that one scaled, you can see that your m should be bigger than your n. Okay, again, m is the distance to focus, n is the distance to the directrix. Or let's say I will consider this one, this vertex here. The distance to focus is your m, the distance to directrix is n. So again, m is always in hyperbola, m is always bigger than n. So you will end up there with a ratio which is greater than 1, which is true to hyperbola. Okay, so that is your hyperbola. Okay, so if this is your major axis, or we call this one the transverse axis. Okay, transverse axis. We have a perpendicular to that as the minor, or we sometimes call that one also in your hyperbola as the conjugate axis. So 2a here is your major axis, or that is a transverse axis. Your 2b there is your minor axis, or we call that one as conjugate. Why is it conjugate? Because actually that divides your first curve with the second curve. Just like on a if you try to relate it with the definition of conjugal, if you say conjugal, it is a joint of two. For example, conjugal property. It is a joint property of the couples, of the two couples. Conjugate. So again, that is your conjugate. It means that is the divisor of these two curves. Okay, your conjugate axis. Why is it that transverse? Because actually it is passing the both curves, so it is the transverse axis. Or by simply knowing that the vertex to vertex is your major axis, or that is transverse, then the perpendicular to that is your minor, or it is the conjugate. So again, just like a while ago, your center there is HK. Okay, so again, your directrix, a while ago, your directrix is farther than the focus from the center. Why? Because it is opening towards this center. But this time it is opening away from the center. So now they will interchange. The focus will go here, will be farther. So C is farther than D. Okay, directrix will be nearer your C. The same as on the other curve, because again your axis will just be dividing your curves into symmetrical. So major axis determines or will actually be dividing your curves into symmetry vertically, and your minor axis will divide your two curves which is symmetrically also with respect to vertical. Okay, and then again, what are the other here? Before we will go there is your, let's try first to discuss your other parameters. See, there is the HK, that is your center. And then B there is the vertex, of course. And then 2A major, 2B is minor, semi-major, semi-minor. L is the latus rectum, so this is your latus rectum, and that is also a latus rectum. C there is the same, center to focus. That is your C. D there is your center to directrix. Okay. Actually, if you'll try this box here is actually imaginary, but that will determine as the major and minor axis. So this box is actually imaginary. But okay, what is the additional here is that if I will consider a line that is passing at the center, two lines passing at the center, which is actually almost touching these two curves on opposite directions, we call this one asymptote. And that is also another line passing at the center, almost touching opposite sides of the curves, and that is also asymptote. So there are two asymptotes. What is asymptote by definition? Okay, asymptote is a line that serves as a boundary. I forgot to include it here, but since we do not have space, but asymptote is a line which serves as a boundary for a curve. So if you say it will serve as a boundary, it means that this curve, by the way, this is our hyperbola, guys. This is the red one. So if you will try to continue that one, that will never ever surpass or intersect your asymptotes. So this asymptote will serve as the boundaries of our curve of our hyperbola. So again, even if you will continue this one to that point, this one, and so in that one, this red curve will never ever surpass our asymptotes. Okay, so that will serve as our boundary. So this is also important in your hyperbola, your asymptotes. And again, asymptote is passing always at the center, and of course it will pass, as you can see, it is actually connecting the corners of your rectangle if you are considering the rectangle. So rectangle, it will pass the corners of rectangle, opposite corners. And okay, later on, if you need to solve the asymptote equation, this is just a line, guys, and we have a given point if ever you already know the center. If already you know the center, which is a point on the curve, what we need is another point, or what we need is the slope. And actually, what we can get here is the slope. Why? Let's say I will consider this point here. 2 points. I will that the slope is rise over run, isn't it? From this point going to that. So rise is actually, the rise of that is actually b. Or even if you will consider this line here, the rise is still b, but it is going down. Isn't it? Right? Rise is or the delta y is equivalent to b. Delta x is equivalent to a. So that is our slope. Slope is, okay, I will explain that one later on. Slope is, I wrote that one on the next slide. Slope is b over a. It could be a positive or negative. Of course, if that is positive, the line is going up. Since that is going up and that is going to the right. And then the slope is negative if your asymptote is the one falling down from left to right. This is rising from left to right. Why? Because this rise is negative going down, isn't it? And that is positive. Okay. So what else? Latus rectum and so on and so on. So now let's try to talk about the general equation of that. In your ellipse, they both exist and they are different numbers. Okay? They both exist and they are different numbers but the same sign. And ellipse, in hyperbola, that is also, they both exist but they are opposite signs. Okay? A and B exist, but they should be opposite signs. So it's either A is negative or B is negative, or of course, Even if a is negative, if you will try to simplify, always isn't it that positive first term? So even if a is negative, multiply both sides by negative so that that will be positive. So b will still be negative. So that's it. That's it. A and B exist, but they should be opposite sign. By the way, what if they are equal? A and B are equal, but they are opposite sign. Is that a circle? Actually, no, because in circle, A and B should be equal and the same sign. So it could be that they are equal. If they are opposite sign, that will fall still under hyperbola. Okay? Okay. So again, that is how you will recognize if your equation is hyperbola. There should be x squared and y squared, and they should be opposite sign. That is as simple as that. Now rearranging just this one into its standard form, just like in your hyperbola. Of course, that is minus, so you will expect that you will have this factor of y, perfect square of y, to be minus, and then of course make that as unity, just like ellipse again. You will end up with number squared, number squared. And when do we know? There are again two possibility here. If your curve is opening vertically, your parabola, or I mean your hyperbola is opening vertically, or that is opening horizontally. So how do we know that one? By looking at the A and B again. A is always bigger than B. So if A is below X, that means it is opening horizontally. If A is below your Y, that means it is opening vertically. Okay? So that is your vertical and horizontal hyperbola. Okay, so again, H and K is the center. So that is your hyperbola. Let's try to relate. As I've said a while ago, the same as your ellipse, but only a slight difference in your Pythagorean theorem. So this is still, okay? E is the ratio AD, CD, but this time E will be bigger than 1. So again, let's say you are not given, it is not stated on the problem that your curve is ellipse, or it is not stated to be parabola, or you do not have there the equation to recognize if ellipse or parabola. If the given is eccentricity, you can actually see if eccentricity is bigger than 1, that is hyperbola. If eccentricity is less than 1, that is ellipse. If somewhat eccentricity is given as equal to 1, that is not a central conic, it is a parabola. Okay. And then of course your L is still the same formula as our ellipse. But this time, this is my main point here. The differences that I am talking a while ago. Since isn't it that your C now is longer because C is from center to focus, isn't it? Since focus is now farther than the vertex, so it means that your C is now farther than or longer than A. That is the difference of a hyperbola and ellipse. So if that's the case, how will I relate? Then actually, if I will still connect that vertex 1 to that endpoint of your semi-minor axis, connect that one, that is the same distance as our C. That is true to hyperbola. So that will create that as actually another right triangle. So Pythagorean theorem, your C now is longer, is the longest, so that is your hypotenuse. So that is C squared equals A squared plus B squared. And again, for later on, if you will need the equation of your asymptote, you have that center point. All you need to have is the slope, and the slope will be, again, as I've said, rise over run, B over A. Slope of the asymptote is B over A. That is positive if you are getting the going up line, or that is negative if you are getting the going down line. And you will use the point slope form, you will have the equations of asymptotes. Okay, so that is the hyperbola, ellipse, and parabola. These are the conic sections. So let's try to have an example. Okay, let's try to have an example. Okay, let's try to have an example. So example 1. Determine the parameters of y of this curve and find the line passing through its focus with a slope of 1/2. So in the first place, it is not given if this is what type of conics. And actually, by merely looking at the variable, as I've said, the y squared is only there is no x squared. So that could never be a circle, that could never be an ellipse, that could never be a hyperbola. So there is only one choice, that is parabola. And y is squared while x is not. So it means in one value of x, in one value of x, in a one vertical line, there are 2 points since there are 2 y. So in each vertical line, there are 2 points. So if I will connect that one, that will actually be opening horizontally. But how do we know? Okay, let's say that this drawing is not yet there. How do we know that that is opening to the left or to the right? Transfer that one to its standard form. Okay. So again, determine the parameters. So first, find the parameters of that parabola, and then, of course, we will try to find also the equation of a line that is passing through its focus and with a slope of 1/2. Okay. So transform. Okay. So again, since we already recognize that that is parabola, transform that one into the standard form of parabola. Okay. So completing the square, y is squared. So that will be, if you'll try to go back there, in parabola, the squared should always be on this side. Okay. And in our example, our squared is y. So remain, the y variables will remain here, and everything will go there. So 2x will be negative 2x, 17 will be negative. Completing the square, okay, get the middle number there, which is actually divided by 2 divided by 1. So that is 3 squared is 9. Add it also here. So by perfect square, that is y plus 3, quantity squared. And if you will try to simplify this one, that is 17 plus 9, negative 17 plus 9 is negative 8. But in your formula or in standard form, that should be y only and that should be x only. So this is minus 2x minus, if I will combine this one, guys, is negative 8. Minus 2x minus 8. So factor out your negative 2x, so that should be x only. So negative 2x will be outside, so that will leave us 4. And if you will combine this one again, is negative 8. So factor out negative 2 from negative 8, you will end up with 4. So if you are not sure of that, bring it back, that will be the same. So we have already the standard form, which is y plus 3, but that should be minus, so it means your number here is negative 3. Then that is x minus, that should be minus again, so your number here is negative 4. Therefore, your h is negative 4 and your k is negative 3, which is, since this is parabola, that hk is the vertex. Okay, that is one parameter. And we have there 4a. Do not forget first about the sign. That determines the opening. If we are referring to the lattice rectum, which is 4a, that is just the number, which is 2. So that is your 4a. So that is our latus rectum, or that is equivalent to L also. But since we need the a later on, okay, so divide both sides by 4, so that will be a. So you will have a, which is equal to 1/2. So that is the length from the center to the vertex. Okay, that is our a. And then later on, of course, we need to draw that one. So what is the opening? Look at that. That is negative. But what is negative? It could be opening downward or to the left. But again, since we said that that is y is squared, so this is a horizontal curve or horizontal parabola. So it means it is opening to the left. And actually, you can check that one by drawing later on. Opening to the left. You need to know the opening. And then, of course, if you have the vertex at negative 4, 3, you will have the focus. Since that is opening to the left, okay, opening to the left, you will have the focus to be at negative 9/2, or that is negative 4.5 and negative 3, coordinate of your focus. How do you know that? Because again, distance of the vertex to the focus is a, and we are opening horizontally, and that is opening to the left. So your vertex is on the right, your focus is on the left. So I will subtract a from the, since we are horizontally opening, okay, we will subtract that a from your x coordinate, which is 4. Subtract a, sorry. Yes. Wait. Yes. Subtract a from your subtract a from your 4, which will be negative 4.5. 0.5. Okay, 4 negative 4 minus 0.5, that will be negative 4.5 or negative 9 halves. Subtracting that one. So that we the same y coordinate, because of course they are on the same level. So the same y coordinate. So that is your focus, or actually you can figure that out if you will draw, as you will draw. But you need there your A. You really need your A. So that's it. And then maybe you need the equation of your directrix. If you will draw that one, actually that is just as a vertical line, which is again, that vertical line is a distance A from the vertex. So if your vertex is at negative 4, 3, that line is passing at, okay, 4, subtract your negative 1 half, I mean 1 half. Okay, by the way, sorry, a while ago. If you will try to subtract this one, that will be, yes, subtract. That will be negative. This will be located at negative 3.5. Okay, isn't it? So you have therefore, if you will try to go to the right, add your negative or your 1 half, add your 1 half, you will end up there with, you will end up there with negative 3.5. Or you can rearrange that one so that that will be general equation of line 2x plus 7. So that is your directrix. Okay, so but that is not just what we need. We need to know also a line that is passing at its focus. That's why we need the focus a while ago. So this is the focus, and we want to get the line passing at that with a slope of 1 half, positive 1 half. So using point slope form, since you already have your focus, and then this is your focus, and then of course your slope is 1 half, so point slope form, 1 half equals y minus, that is negative 3, so that will be plus 3 all over x minus, but that is negative, so plus 9 halves or 4.5. Rearranging this one, actually this is algebra already, guys. Again, you will end up with the equation of that to be 2x minus 4 minus 3 equals 0. Okay, 2x minus 4 minus 3 equals 0. If I will draw this one now, I will draw. This is our parabola. These are your latus rectum. Okay, by the way, if you are drawing it manually, it is always better to get the endpoints of your latus rectum, so that will serve as another 2 points of your curve, and then all you need to do is trace from vertex to those end of latus rectum smoothly, and then you will have the drawing of your parabola. Okay, so that is the best way to draw your parabola manually, but since I draw this one in application, then that's it. And then of course drawing your line, this is our line, which is true because the line is passing at the focus, and if you will try to get the slope of that, that should be 1 half. It is positive since that is going up. Okay, that is your example number 1. Okay, let's try to have one more example. Find equation of a horizontal ellipse with center at the origin, eccentricity of 1 half, and distance between the directrices to be 24. Draw the curve. Okay, so what we need now is the equation of ellipse. Actually, even if it is not given to be ellipse, you can say that that is ellipse by looking at the eccentricity, since the eccentricity is given, which is less than 1. So that is ellipse. Okay, and the ellipse is having the center at exactly the origin, and the distance between directrices is 24. The distance of directrices is 24. By the way, if you will try to go there on the ellipse, what is the distance? Center to the directrix is D, and center to the other directrix is D. So directrices, distance of 2 directrices is equivalent to 2D. Okay, so that is your 2D, twice D. So we can actually get the value of D there. Okay, and then of course draw the curve. So first, let's try to draw the parameters completely, the parameters of the curve, and then later on the equation of your ellipse. So given eccentricity to be 1 half, positive 1 half, and then of course your that is 2D again explained because that is the distance between two directrices. So from center to directrix is D, from center to the other directrix is another D. So that should be 2D, which is 24. So getting from this your D, which is 12. Okay, so we have D, we have E. Isn't it? We have three equations available. Four, if you will break this down into two, in your hyperbola and ellipse. So from this one, from this equation of eccentricity, we have E eccentricity and D. So let's pair E and AD. Okay, since we have D and we have E, cross multiply D with your E, you will have the equation of A to be D equals E. D times A is equal to D times E. Your D is 12 and your E is 1/2, so your A is 6. And then again, pairing that E with your C over A, you have A already, you have already solved A, you have E. So solving for C, cross multiply A with your E. C is equal to A times E, which is equal to 6 times 1/2, you will end up with C, which is 3. Okay, which is true because C is always smaller than A, or C is the smallest in your ellipse. In ellipse, C is the smallest. But in hyperbola, that is the other way. C is the largest. Okay. So let's try to solve the others. We have A, C, we have D, we have E. What else do we need? Is your B, your semi-minor. So from your Pythagorean theorem, but this time in ellipse, A is the longest, isn't it? So rearranging this one, you will have B is square root of A squared minus C squared. Substitute, you will have square root of 27, all in all, or that is the exact value. And then of course we need the latus rectum if you are drawing it manually so that you can draw it smoothly. So 2b squared all over a, that is your equation for latus rectum, is 2 there. Your b is square root of 27 square root 1 all over a, which is 6. You will end up with the latus rectum length of 9. Okay, that is 9. And then of course we need the vertices and focus. What we only have is the center, since again it is given that center is the origin, so your center is at 00, but we need to know your vertices and foci. So if your center is at 0, 0, since this is opening horizontally, it means that your other points is located horizontally with your center. So it means that the y coordinate of that is always of the of the focus and the vertices. The vertices and the foci are all y equals 0 because they are of the same elevation, since that is a horizontal ellipse. So again, distance of center to vertex is a, isn't it? So we will deal with your 0 x plus 6. You will have 6 0. That is your vertex on this right side. And then minus 6. 0 minus 6 is negative 6. So you have negative 6 0 vertex on the left side, which is your vertex 1. And then getting your focus, distance of focus to center is C, isn't it? So again, the same, from 0, add 3, that will have 3 0, that is your focus on the right. And then subtract, that will be negative 3 0, focus on the left. So you have the focuses. But if that is vertical, guys, if that is vertical, you should be adding and subtracting your A and C in your y coordinate. So it means A will remain, X will remain 0 if that is vertical. If that is vertical. And then of course we need the directrices later on. Okay, so at center 0 0, your directrix, distance to the directrix D is 12. So minus 0, it will be passing, it is a vertical line passing at negative 12. 0 minus 12 is negative 12, so that is a straight line passing at negative 12. And then that is a straight line. If I will get the directrix on the right side, I will add 12. 0 plus 12 is positive 12, so another vertical line at x equals positive 12. And then you have already the parameters completely, so we need to get the equation. So where do we start? Of course, it is a reverse process. We are getting the general equation, so we will start from standard. If you have the equation and getting parameter, transfer to standard form. But this time, we will start with standard form, transfer to general form. Okay. So what will I use? A below X or A below Y? Because that is horizontal. A is below your X. It means that your major axis is parallel with X. Okay, so substitute. H and K, by the way, is 0, 0, so that is useless. But A there is 6, and then B there is square root of 27. So substitute. X squared all over square root 6 is 36. Y squared all over square root 27. It will cancel, so you have 27 equals 1. But that is of course not the uh, general form. So rearrange. LCD of that is 108. And then of course 108 divided by 36 is 3. So 3x squared. 108 divided by 27 is 4. That will be 4y squared. And we do not need a fraction, so cross multiply that on the other side. This will go 108 on the other side. So rearranging that one, you will have this as the general equation of our ellipse. And then draw, of course, draw the curve and this one. So you have here your center. That is what I'm saying. The distance from center to focus is 3. So going to the right is 3. Yes, you will have there 3, 0. And going to the left is negative 3. So you have negative 3, 0. And then from center to vertex is A. So A is 6. So going to that is distance 6, and going to that is still distance 6. And then B is your semi-minor, so square root of 27. So your X is still 0, isn't it? Because that is the same vertical line. But 0 plus square root of 27, it will be positive square root of 27. So you have 0 positive square root of 27, and below is 0 negative square root of 27. And then later on, you will be needing for you to be having a smooth curve, you will plot the endpoints of your latus rectum. Latus rectum is 9, isn't it? So if I will divide from focus, you will draw your latus rectum. But your latus rectum is from the 2 points on the curve. So dividing it to 2 so that you will refer the distance from the focus. 9 divided by 2 is 4.5. So this is 3, 0. 1 point on top is 3, 4.5. That is your distance of half of the latus rectum. Subtract your 4.5, that is 3, negative 4.5. And here the same, that is negative 3, 4.5, negative 3, negative 4.5. So trace that one, that is our equation. And this is your directrices. Passing at x equals positive 12, x equals negative 12. I just rearrange the equation into the general. Okay, so that is our examples. Okay, you have an activity, and actually that is hyperbola. So solve that activity, applying of course the equations and the general equations and standard equations of hyperbola, and so with the relationship of parameters. Okay, so that's it. That is your hyperbola. Okay, so are there any question? Comment that below the video, and then of course for our credits. So thank you very much for watching.